Shall we start? So I would like to welcome you to this last Fmics session, which is a session on test generation and probabilistic verification. We will have two presentations in these sessions, and the first one is on PsyTallyRo, which is a search-based test generation for CPS implemented in Python, and the talk is given, if I'm not wrong, by Quinn Thibault.
Hello everyone, my name is Quinn Thibault and I'm from Arizona State University. This presentation is about PsyTallyRo, which is a Python toolbox for search-based test generation for cyber-physical systems. Let's begin with semi-formal verification. As technology advances, the number of cyber-physical systems is increasing. As systems become more sophisticated, they can begin to make decisions based on unknown or non-deterministic internal processes. Even systems without these internal processes can be sufficiently complex to make behavior prediction difficult. These factors make it hard to guarantee correctness, which is especially problematic for safety-critical systems where an error at runtime could potentially cost lives or capital. Semi-formal verification is a framework for testing systems that attempts to guarantee that incorrect behavior will never be observed. Initially, semi-formal verification tools were developed in MATLAB to use models targeted by the industry developed in Simulink. Unfortunately, this creates a dependency on the MathWorks ecosystem and can make supporting other platforms difficult. As the industry moves towards autonomous vehicles and artificial intelligence, the use of Python is increasing, in part due to its large ecosystem of libraries for robotics and machine learning, as well as robust support for interfacing with other languages and systems. Python's language design enables rapid development, and its runtime type system encourages modularity and extension via duck typing. One area of active semi-formal verifications research is falsification, which is a semi-formal method with a formal requirement. The ARC competition is held every year since 2016 to allow teams to compare their falsification tools using a standard set of models and requirements. Why is falsification semi-formal? While the method is constrained by a formal requirement, the model of the system under test may not always be completely defined or may be too complex to be evaluated using formal methods. By relaxing the requirement of a fully defined system, the falsification method makes it easier to implement tests by allowing testers to focus on specific system behaviors. In practice, this method can still reveal system errors without requiring the system to be fully described. Falsification is the process of searching for falsifying behaviors, that is, behaviors that do not satisfy the requirements of the system. Requirements can be described using signal temporal logic, or STL. The STL grammar is composed of the traditional Boolean operators, as well as several temporal operators like next, eventually, and always. Temporal operators like always and eventually can include an optional time interval to restrict their application. STL requirements also include predicates, which are Boolean expressions that represent a requirement of the output. In the time interval example, the symbol A represents a system output, and the inequality A greater than or equal to 10 is a predicate. Evaluating a system's outputs using an STL requirement yields a robustness value, which is a scalar that indicates how close the system came to the falsifying region. A negative robustness value indicates that the system violated one or more predicates and entered the falsification region. Now we will discuss the architecture of the PsyTallyRo package. There are 4 components that must be provided in order to run a test: the model, the specification, the optimizer, and the options. The first component we will explore is the model. A model is a representation of the system under test, which can be implemented using techniques such as software in the loop, hardware in the loop, physical measurements, or more. A model is evaluated by providing the static parameters and signals generated by the optimizer. Static parameters are time-invariant inputs to the system, while signals are time-varying inputs. The output of a model is an array of states representing the system trajectories and a corresponding array of time values. The output of the model is passed to the specification to compute the cost. As previously stated, signals are time-varying inputs to the system, which are constructed from the sample generated by the optimizer. The sample is decomposed into the static parameters and signal values as specified in the options object. Then, the signal values are combined with a fixed number of time values to create interpolation functions called signals. The type of interpolator of each signal is specified in the options object and can be extended to use custom types of interpolation. The next component is the specification. A specification represents a single requirement of the system and is responsible for evaluating the output of the model and returning a single scalar value called the cost. The cost indicates the goodness of the model output with respect to the requirement. The cost value is returned to the optimizer, where it can be used to inform the selection of another sample. Internally, the model and specification are composed to create a cost function that is used by the optimizer to evaluate samples. The cost function is also responsible for maintaining a history of every sample it evaluates. For increased flexibility, the cost function can evaluate one or many samples, either sequentially or in parallel. The role of the optimizer is to attempt to minimize the cost function of the test. Samples are selected from a multi-dimensional sample space where each dimension is a static parameter or signal value defined in the options object. The options object also provides to the optimizer a sample budget that indicates the maximum number of samples that the optimizer may select. Sci-Tally-Row defines two behaviors for optimizers: falsification and minimization. Under minimization, the sample budget is always exhausted, while under falsification, the optimizer is stopped when the first negative cost value is found. The final component is the options object, which configures the behavior of all other components. Some common options of the options object are static parameters, which are the time-invariant inputs to the system, signals, which are the time-varying inputs to the system, runs, which is the number of times to execute the optimizer, iterations, which is the sample budget, behavior, set to minimization or falsification, the seed, which is the input to the random number generator and is included for repeatability, and parallelization, which indicates the number of processes to use to execute optimizer runs in parallel. Now we will discuss some of the component implementations included with the Sci-Tally-Row toolbox. The Sci-Tally-Row toolbox provides two types of models. The first model is called a black box model. The black box model does not make any assumptions about the underlying system that it represents. The black box model interpolates the signals according to a sampling interval. A black box model is constructed by providing a function that accepts three parameters: the static parameters, the signal times created from the sampling interval, and the signal values created by evaluating the interpolators at each time step of the signal times vector. A black box model is required to return a simulation result or falsification instance. The second type of model that Sci-Tally-Row provides is an ODE model, which assumes that the underlying system is represented as an ordinary differential equation. An ODE model is constructed by providing a function that accepts three parameters: the time, the state, and the signals. The ODE model is required to return a vector that represents the derivative of the state at that current time. Users can implement their own models by inheriting from the base model class in the Sci-Tally-Row package. The Sci-Tally-Row package provides three different optimizers. The first optimizer is the uniform random optimizer, which randomly selects samples until the sample budget is exhausted. The uniform random optimizer can be used for Monte Carlo sampling. The second optimizer is the simulated annealing optimizer, which implements general simulated annealing and is built using the SciPy library. The third optimizer is the Part X optimizer, which is a family of stochastic optimizers with probabilistic guarantees. Part X estimates the probability that falsifying behavior exists, even when no falsification is found. Part X is an open source package and is available at the following URL. Users can also implement their own optimizers easily by inheriting from the optimizer class in the SciTallyRow package. Finally, SciTallyRow provides 3 specification implementations, all of which use signal temporal logic requirements. SciTallyRow uses 2 different libraries to provide robustness computations for STL. The first is TLTK, which supports STL/MTL requirements. It is an offline monitoring package and has optional quadratic programming optimization. TLTK supports parallelization for fast robustness computation of long multidimensional trajectories and is an open source package available at the following URL. SciTallyRow also uses the RT-AMT library for robustness computation, which supports STL or LTL requirements, and is also an offline monitor which supports discrete or dense time semantics. RT-AMT is a pure Python implementation with an optional compiled component. RT-AMT is an open source package available at the following URL. Users can also implement their own specifications by adhering to the interface defined in the SciTallyRow specification module.
Here is an example of a SciTallyRow script which is used to run an F16 GCAS simulator. The first section of the script is the model definition. This function is decorated to construct a black box model. After some initial definitions, the function constructs and executes a simulation of the F16 GCAS system using the static parameters generated by the optimizer. After defining the model, the requirement and specification are constructed. In this case, the requirement is simple: do not hit the ground. The specification is constructed using the requirement and a dictionary which tells the specification which column of the trajectory data to use as the altitude value. The next section is the optimizer definition. In this case, we select the uniform random optimizer. The final configuration section are the initial conditions and the options. The initial conditions are created as an array of pairs comprising the lower and upper limits of the parameter interval. Then, the options object is constructed, specifying the relevant information. When an option is not specified, a sensible default is provided. In this case, we've elected to only execute the optimizer once with a budget of 10 samples. We set the simulation interval to be from T0 to T15. The STallyRow function then executes the test using the 4 previously defined components and returns a result object which houses the outcome of each optimization run in the runs attribute. Each run has an evaluation history which we iterate over to print the sample and the associated cost.
For additional information about the SciTallyRow package, please visit our documentation site or our repository. You can submit issues or download specific versions of the SciTallyRow package. Some future areas of further development are parameter mining, finite state machine support, online monitoring, and conformance testing. This project was sponsored by the following DARPA and NSF grants.
Thank you very much for the presentation. So you can write your questions in this Q&A using this Q&A option. And I'm not sure how it works, whether people can also raise the hand and ask the questions orally.
Or they can use the chat as well.
Okay, thank you. So please, if you have a question, please feel free to write it either in the chat or using the Q&A button. In the meantime, while waiting for the audience, I would have a question. And what are your plans in whether you plan to support additional types of models. So I guess the ODE model is that you can follow also gradient descent. Is it correct? Do you see also any need to support something in between the ODE and the fully black box models in the future?
So there are some plans to support additional models, both for ease of use and for additional functionality. One thing we've been very interested in is supporting finite state machines, which would need to be represented as their own model because there's some intrinsic architecture that would require, or some architecture changes that would be required. And then for convenience, it would probably be easy at some point to provide MATLAB or Simulink model wrappers just to help people out interfacing with different systems without having to write their own code.
Actually, this was my second question. So MATLAB Simulink supports Python. And did you try out comparing S-Taliro to Psi-Taliro in terms of performance, quality of results? Did you do any experiments on running the same Simulink models, but one with the falsification using the S-Taliro and one using the Python library?
We haven't done any head-to-head comparisons. We did test the Psi-Taliro package with the same ARC benchmarks that S-Taliro was provided against, and we found the same kind of falsifications, but we haven't done any head-to-head comparisons, no.
Thank you. And this is your last chance. Okay, we have a question. What are the restrictions on the objective function? Can one, for example, try to minimize energy consumption?
So the implementations that we provide are very specific, but as long as the interface, the specification interface is adhered to, technically any kind of arbitrary analysis can be performed. So it's perfectly feasible to create a custom specification that could minimize energy consumption rather than robustness, for example.
And maybe one last question from my side. Do you plan to do any multi-objective optimization?
That is something we hadn't discussed, but is I think definitely an interesting direction to go, and would definitely be something I would like to explore further.
So I would like to thank again the speaker for this very nice talk, and we are moving to our last talk, and this is about the probabilistic verification for reliability of a 2x2 network on chip system, and the talk is given by Riley Roberts.
Hi, my name is Riley Roberts, and today I'm going to present on probabilistic verification for reliability of a 2x2 network on chip system. This is a joint work between myself and the other authors listed here on this slide. To begin with, as the complexity advances in designing reliable distributed many-core systems, network on chip has become the de facto standard for on-chip communication. Network on chip is often referred to as a NoC. Now, NoC design faces unique reliability challenges that some other systems don't, such as process variation, which is the variation in the transistor attributes, as well as environmental variation, which refers to the change in the supply voltage and temperature. Up until this point, NoC verification has focused primarily on functional correctness, and probabilistic verification has not yet been applied to the NoC domain. However, recently, advances in probabilistic verification have produced many mature tools, such as the Modus toolset, the Storm model checker, and the Prism model checker. And here we intend to utilize some of those advances to apply it to the NoC domain. In this paper, we present our probabilistic verification of power supply noise for a 2x2 mesh NoC with uniform random distribution of the incoming Flit destinations. And a more detailed description of power supply noise will come on the next slide. We also present the cumulative abstraction techniques we applied, including a novel probabilistic choice abstraction. And then we additionally give our insights to design decisions that significantly impact PSN. PSN, or power supply noise, can radically degrade the delay of various on-chip circuit components, which in turn causes timing errors in the pipe stages of the NoC routers. PSN is primarily composed of two components, the first being resistive noise, which is the product of the current drawn and the lumped resistance of the circuit, and the second being inductive noise, which is proportional to the rate of change of current through the inductance of the power grid. All of the formal models presented here in this work were developed in the modest modeling language and then checked using MCSTA for probabilistic model checking, which is the probabilistic model checker of the modest toolset. Additionally, we use some statistical model checking using modes, also a tool from the modest toolset. Here we present the NoC that we used to build our concrete formal model. As you can see, it's a 2x2 NoC consisting of 4 routers, here labeled 0, 1, 2, and 3, and represented by the larger square boxes. Each router consists of 3 buffers, each with 4 slots. Within this system, each router has access to 3 separate channels, one coming from what we term local, or the other parts of the system outside the NoC, one in the horizontal or east-west direction, and one in the north-south or vertical direction. It uses these channels to send flits to the other routers where they are then stored in the buffer until they can be processed. You can see with this red dot here the way that one flit might move through this particular network. It can come from the local channel into router 0 and be placed in its buffer. Assuming this flit has a destination of router 3, we use XY routing to first, in the next clock cycle, route it to router 1, where it will be placed in router 1's east-west buffer, then be routed to router 3 in the next clock cycle, after which it will be routed back into the original system. Each router also consists of an arbiter. The arbiter is used to determine which router gets to use the channel in case of multiple buffers wanting to use the same channel. For example, in router 0, if there was one flit in the east-west buffer and another flit in the north-south buffer, and both wanted to send in the local channel, only one would be able to during a particular clock cycle, and the arbiter which would determine which of those would get to. This figure here shows how our arbiter determines which buffers should get to send on a particular clock cycle. We use a round-robin arbitration of conflicts, which indicates that after a channel gets a turn, it moves to the back of the line as far as the priority goes. To illustrate that a little more fully, we can look at this first example here. Here we see that there are 3 channels, local, east, and south, and they are arranged in a priority ordering in time t equals n, which is a particular clock cycle, with local being the highest, followed by east, then south. Unserviced is a variable indicating whether or not that particular buffer got serviced in this clock cycle. Here we can see that local and south both did not get serviced. Our algorithm works by moving all unserviced buffers to the front of the queue while maintaining their original ordering. So here local remains at the front in the next clock cycle, while south moves in front of east in the ordering because east was serviced. The formal models presented in this paper are all developed on a behavioral level. So in order to model check or reason about power supply noise, we also need to map power supply noise onto a behavioral level. We did so by considering first each component of PSN. For resistive noise, we incremented a variable anytime all 3 buffers of one router send a flit during the same cycle, which corresponds to high router activity. Similarly, for inductive noise, we increment a variable anytime a router goes from sending no flits in one cycle to a resistive noise event in the next cycle, or vice versa, indicating a large change in router activity. Due to the large number of variables present in the concrete model, enumerating all of the states for model checking is infeasible. Instead, we bound the model checking by a certain number of clock cycles in order to limit the state space. Unfortunately, the concrete model does exhibit exponential state growth with respect to the number of clock cycles considered. So we applied cumulative abstraction techniques in order to make the problem more tractable. The first abstraction that we used was a simple predicate abstraction of the data structures. All variables and complex data structures in the model were simplified down to predicate variables. This allows for easier analysis and helps us to determine further abstractions as well as allowing the model checking tools to be more performant as they don't have to deal with the complexities of the data structures. Here we can see how we did this mapping, where we have a Boolean variable R0L1. R0 corresponds to router 0, which matches the previous data structure here, NoC, with the 0th index. L indicates the local channel, as we can see here, and 1 indicates that that was the east direction. We did this with all of the complex data structures in the model. Next, we present our novel probabilistic choice abstraction. The background of this abstraction is that all flit destinations are chosen from a known probabilistic distribution, in our case the uniform. Also, this destination information is only used to determine the forwarding direction of the flits, but has to be stored throughout the entirety of the flit's lifetime. The idea is to delay the probabilistic choice of the destination from the time of input instead to the time of forwarding. What this does is remove the destination information entirely from the state space and instead replaces the forwarding decisions with a probabilistic distribution of their own, which can be derived combining the original distribution with the routing protocol. Here we show a simple model in order to illustrate exactly what the probabilistic choice abstraction does. This model contains 4 variables, x, y, z, and clock. X can be 1, 2, or 3, y can be 1 or 2, and clock cycle increments each time. Z will be determined based on the values of x or y. Here we see that the initial values of x and y are decided using a probabilistic distribution. Here it's simply a 1/6 probability of all the different possible combinations of the values of x and y. Following that, we apply different logic to update z based on the values of x and y. Since we know the values of x and y in this middle row here, we can directly achieve the next state with z's new value in this final row. The goal of this abstraction is to preserve the behavior of z and with respect to clock. Similarly, in our model, we have the goal to preserve the behavior of our resistive and inductive noise variables with respect to the clock variable. Here, Because we know that z is going to be updated based on the information of x and y, we first analyze how x and y are determined. They are determined here with this probabilistic distribution. If we remove x and y from the state space, this first transition here becomes a simple transition in our new model because z simply remains the same in clock cycle increments. In the next step, however, we need to determine how z can be chosen to be 0, 1, or 2. If we analyze the first model, we can follow the traces that result in z equaling 0, 1, or 2 and sum their probabilities to get their probabilities in the new model. Similarly, we can do this mathematical analysis for more complex problems, such as our particular situation, in order to remove the destination information from the state graph. Following the probabilistic choice abstractions, other simple abstractions became available that previously weren't or were harder to notice. One of these is that there are 6 total priority orderings, but only 4 of them affect the behavior because 2 of the buffers can never be in conflict with one another. So rather than encoding all 6 into the state graph, we can simply keep track of the 4 that matter. Additionally, now that we don't have destination information, each flit is represented in the buffers as a simple Boolean indicating whether a flit is present there or not. Rather than keeping an array of Booleans as the buffer, we can instead encode the buffer as a simple bounded integer representing the current length of the buffer, where 0 is empty and 4 is full. This figure here shows the different state space growth rates of the models after various abstractions. Remember, these abstractions were performed cumulatively, they're not individual. Here we present particularly the results under an every other cycle flit injection pattern. This pattern is one where every router receives 1 flit from the system every other cycle, and all 4 routers receive that 1 flit simultaneously. Under this load, we can see that the concrete model exhibits very fast state growth, reaching upwards of 20 million states after only 4 clock cycles. The probabilistic choice abstraction is the first abstraction that significantly lowers the rate of state growth, and then applying the additional Boolean Q abstraction lowers this even further. This figure here shows the results of our model checking our PSN-related behavior for the every other cycle flit injection pattern. Unfortunately, despite all the abstractions, we are still only able to check for up to 30 clock cycles. However, in the 30 clock cycles here, you can see that the probability of even one of the, say, resistive noise events is on the order of 10 to the negative 4 after 30 clock cycles, which is relatively low. We also use some statistical model checking in order to simulate the behavior over a longer number of clock cycles, since we could not check for very many, and we confirmed that there is a relatively low amount of PSN behavior even over a large number of clock cycles. In the real world, flits are more likely to arrive in a burst than in an every other cycle pattern. We were able to check bursts of 1, 2, and 3, where the number of idle cycles are at least twice the burst length. When we allow the idle cycles to be at least twice the burst length, it lets the entire NoC system reset between bursts to the original state. This results in vastly increased scalability, where we are actually able to check for an arbitrary number of clock cycles and need only bound the resistive noise and inductive noise variables. These graphs show the cumulative distribution function for the probability of various levels of resistive noise and inductive noise events for a burst of 3 flits out of every 10 cycles. Once again, all of the routers receive the 3 flits on consecutive cycles at the same time. Here we can see that after the 30 clock cycles that we originally checked with our every other cycle model, this model results in a much higher probability of a resistive noise event, despite 3 out of 10 flits actually being less total flits every 10 cycles than the every other cycle flit injection pattern. Similarly, when we checked a burst of 1 out of 3 flits, we found that there was 0 probability of PSN events over all of time. Once again, this is more total flits than the 3 out of 10 injection pattern, but with no PSN in comparison to a relatively high amount of PSN for the 3 of 10 injection pattern. This shows the impact of the design decisions on the PSN of the system, particularly that input patterns can minimize PSN without requiring lower system load. So the total amount of flits that enter a system does not have to be reduced at all, and the system can still have lower PSN, resulting in less erroneous behaviors. In conclusion, we found that model checking the concrete formal model of this NoC is infeasible, but that repeated abstraction techniques can make the problem more tractable. We also show that design decisions can greatly impact power supply noise, and recommend between flits entering the NoC in order to minimize PSN. For example, if a NoC is known to receive about 30 flits every 100 cycles from the rest of the system, it would be better to send those flits 1 out of every 3 cycles over the course of the entire 100 cycles than to send all 30 in a burst, as far as power supply noise is concerned. As future work, we plan to formally prove the probabilistic choice abstraction, as well as apply these methods to larger NoC configurations. Thank you.
Thank you very much for this presentation. Let me ask the audience to write your questions either in the chat or in this Q&A box. While we are waiting for the audience to ask you, I would like, I was wondering, you mentioned that you also did some statistical model checking on the longer traces, and what I would like to know is whether there were on this shorter trace number of cycles, some insights that were given by the exhaustive technique that you would not see using the statistical model checking in this particular case study.
Yeah, so for this particular case, I showed, you can remember that there was a really low probability of the events associated. Because of that, in order to accurately capture that probability, you would have to run a really large number of statistical runs just because the true probability is so low. And so in order to get any valid information, we had to do quite a large number of runs, as well as for a large number of clock cycles. And if we wanted to do it for the shorter number of cycles like we did with our exhaustive check, you would have had to run a significant number of runs in order to get those values, just because there are such rare events.
Thank you. So would it make sense to combine then both techniques?
Yeah, it might actually, where probabilistic verification could be used for the short-term behavior that statistical model checking can't get quite as well. And then add on the statistical model checking for that long-term behavior that is sometimes infeasible computationally with the model checking.
So we also have a question from Jaco van de Pol. He's thanking you for the nice talk and asking if there is a formal or experimental justification for the correctness of the abstractions.
So we are working on a formal justification that is currently in progress, but is not yet completed. But we do have an experimental justification where we were able to observe identical probabilities for up to a certain number of clock cycles. After a certain number of clock cycles, the measured probabilities do start to differ just slightly. We believe that's due to some floating point errors because of how small the difference is and just the overall difference in the architecture, but we are investigating that further as well.
Thank you. And then we have another question from Garavel, are there other applications of probabilistic statistical model checking to NOCs, or is your work the first application of such techniques to this application domain? NOCs seem to be a killing application.
So as far as our knowledge is concerned, this is some of the first work in the probabilistic model checking domain. I'm not sure in statistical model checking. There was an earlier work by some members of our team to analyze a single router of a NoC that was presented a couple of years ago in Fmics. But to our knowledge, we are some of the first to be doing probabilistic model checking of NoCs.
Thank you very much. I give to the audience the last chance to ask a question to Riley. And yeah, let me thank you again for this very interesting, very nice presentation. Actually, now I would like to announce the end of this session and to give the floor to Anastasia and Alberto.
Thanks a lot, Dejan. Thanks a lot to all the speakers and to the audience to be here. Last day, last session, late for the Europeans, much more late for Russians, from people from Asia, and okay, the US guys, you still have the entire day in front of you. Thanks, Dejan, for chairing the session. So it's coming to an end, so I will share some final set of slides. Let me see here. And just to say, let me see, what is the bottom here? Present. Yes. Can you see my slides?
Yes.
Okay, there is not much we have to say. This is coming to an end. It has been a pleasure to be with you. We have enjoyed a lot of talks, discussions. We had a keynote. I know that you are going to miss us, but if you do, please remember that all the videos, or most of them, will live forever and on YouTube, at least as long as Google and YouTube exist. And of course, you still have also the proceedings. So if you tonight you are looking for something to read before you close the day, you have the nice volume with all the papers that will hopefully survive forever. Good. It's also the moment to announce the Best Paper Award. This is, of course, both a pleasant and unpleasant thing that Anastasia and I had to do, because really we think that we have collected a very nice set of papers, and the presentations were even better. And so it was hard to make a choice. We have listened to the opinion of the program committee, both during the discussion, but also while there is a raise, a hand being raised. So I don't know. I cannot see you guys. So if there is something that you want to say, I have to. I see. Okay, nothing. So we listened to the PC, the opinion in the discussion of the papers, and then we saw the presentations of the papers. We also listened to the opinion on the presentations, and at the end, Anastasia and I had to make a choice. And just before I anticipate the choice, let me share two examples of sentences that the awarded paper got. The first one says that the paper is very relevant to Fmics. It shows a good example of how formal methods can be applied for industrial applications. And this is something that both Anastasia and I share, that this paper really is a good example of how papers for Fmics are expected to be, given this forum and the goal of this forum. And the second sentence along the same lines is a bit more specific, but it says that this work is definitely of industrial interest for both legacy and new ladder programs to be developed. So I guess that the authors already know which paper it is, and part of the audience also perhaps have guessed. The paper is Automated Verification of Temporal Properties of Ladder Programs. by Claudio, Denise, Florian, Claude, David, and Hioraki. Congratulations, guys. Would be nice to see you, but I cannot see you. So I don't know if we can, hear someone clapping, because I mean, I feel a bit alone here. Let me see if I have more slides. Yeah, it's okay. Maybe we'll move to the next slide. Anastasia will say some words, and then perhaps we can find a way of clapping all together and celebrating with the authors of this paper.
Yeah, congratulations to the authors. We would really like to thank everyone that made the Fmics possible. We are grateful to the steering committee for the continuous support and help. We thank the PC members and sub-reviewers for excellent and timely paper reviews and discussion. We are grateful to the Confest organizers for hosting the website and organizing all the virtual aspects of the conference. We thank the authors for submitting their work at Fmics and for the great presentations. We thank our keynote speaker, Joe Kiniri, for a very inspiring and motivating talk. And last but not least, we're grateful to all session chairs and participants. Despite not being able to meet all of you in Paris, we hope that you enjoyed Fmics this year as much as we did. Next, I will give the floor to Jaco van de Pol, that will make an announcement from the steering committee.
Thank you. I'm trying to share a screen, but is that possible? Maybe not.
Yes. Try again, please.
Yeah. Okay, thanks, Anna. So I just need 1 minute for the closing of this Fmics 2021 session, because you have thanked quite a lot of people, but I think you forgot 2 people. So let's extend the thanks to the chairs of Fmics 2021. And this is not a true image of the chairs, maybe, but this is a nice image of chairs somewhere from Denmark. But here are the chairs. So thanks a lot on behalf of the steering committee for all the work. It's a lot of work to organize a conference. It starts with planning, with finding a PC, with advertising, and trying to get nice papers. And you succeeded quite well this year in gathering a really nice collection of papers. And then the reviewing, quality control, things have to be published. And then there's the conference itself, which happened over Zoom, finding the session chairs, etc. So it has been a lot of work, and we are very grateful that you did a wonderful, good job and made Fmics 2021 to a success. And now you are mostly finished, nearly finished, not completely finished, because you will still look into a special session, a special section for a journal. So there is still a little work remaining, but the bulk of the work has been done. So thanks a lot. I have one more slide, and that's about future. So what will happen in 2022? I think most of you can guess, because Fmics will join Confest again in 2022. So we started the tradition 1 or 2 years ago, and we think it's a very nice tradition. So we'd like to continue this. So Fmics 2022 will be co-located to Concur, which happens 30 to 16 September. So Fmics will be around the same time. We have not yet decided the exact dates. And where will this happen? You probably know, but this will happen in Warsaw. And the idea and proposal is to have a physical conference again. So let's hope that it's possible. So thanks for giving me the stage for these seconds. Thanks. And
thanks a lot, Jaco.
Yeah. Thank you.
And thanks a lot also to Bogdan, that has been here. I think you have been always with us, Bogdan. So that's been very, very, very useful, very helpful. Can I perhaps ask you?
Thank you very much.
Can I perhaps ask you for a last favor? Do you think it's possible to invite all attendees as panelists so that we can see each other and say goodbye in a more human way, or is it technically too complicated?
Let's try.
Yes, select all and invite. I don't know if it works, but we can see some faces perhaps and say goodbye.
Maybe we can take a photo.
Yes, also, but
screenshot.
Yes, everybody fix. Yes. Not. Yes. Ah, okay, we're getting some panelists, but let me see, can we see some faces? Ah, okay, that's fantastic. Right, nice. I see some people here, some of the speakers, and I guess. Thanks to everyone. We should have done this in every session. I can see also Benoit. Okay, we have a lot of people here. Fantastic.
Alberto. Well done.
Yes. Only Diego is missing. If Diego activates the camera and points at some less darky.
Yeah,
yes. Okay. Let's take a screenshot of this. Okay, fantastic.
Great job.
Hi guys, have a nice time and enjoy the rest of the day, enjoy the rest of the week. There is still some conference things happening, so.
Yes, guest is finishing in a few moments.
Yes. Bye-bye, everyone.
Bye-bye. Thank you. Bye-bye. Bye, everyone.
Thank you so much.
Thanks,
Bye-bye.
everyone.
Bye-bye.